M is the mass of the object. G is the acceleration due to gravity. On Earth, it's 9.8, or we use 10 meters per second squared. And H is the height. One important thing to note is that when you calculate the gravitational potential energy, you have to calculate it relative to a certain position. Here's what I mean. If I have a block on the floor, and this block has a mass of 1 kilogram, I can say when it's on the floor, it's all the way down. The potential energy, the gravitational potential energy, is 0 here. And then I lift it up 1 meter, and now it's up here. If I drop it from up here, it's going to change this potential energy it has into kinetic energy as it comes down. The potential energy, the gravitational potential energy it has here, is its mass, which is 1 kilogram, times G, which is 10 meters per second squared, times the height, which is 1 meter, measured from the floor, which is 10 joules. So we can say relative to the floor, the block has a potential energy of 10 joules. If I lifted it up another meter, now it's 2 meters above the floor. I'll have the same mass, the same G, and now we'll have 2 meters. So this will give us a potential energy of 20 joules. Or we can think of it like this. We can say, well, we have a table that's up here about a meter above the floor. That's the table's leg. Let's make it go all the way to the ground. And we put the block on the table. Maybe I want to say when the block is on the table, the gravitational potential energy is 0. And I can do that. I can choose the potential energy to be 0 at any place. Then if I lift it up another meter, up here, the potential energy is going to be, plug in all these numbers again, 1 kilogram times 10 meters per second squared times 1 meter, because it's 1 meter above the place where we said the potential energy is 0. So this is 10 joules. Likewise, if it falls down 1 meter, it will land, just before it lands, it'll have a kinetic energy of 10 joules. It's given up 10 joules of potential energy. So the potential energy is now negative 10 joules. Potential energy can be negative. Work can be negative. Kinetic energy can't be negative because mass is a positive, has to be positive or 0, and v squared can't be negative either. Let's try a couple problems. A 0.6 kilogram basketball is dropped out of a window that's 6.1 meters above the ground. The ball is caught by a person whose hands are 1.5 meters above the ground. How much work is done on the ball by its weight? So work is force times displacement times cosine of the angle between them. So in this case, the force is gravity. This will be mg times d times cosine. Let's see, gravity pulls down, the ball's going down, both in the same direction. The angle between them is 0. Cosine of 0 equals 1. So we just have work equals mgd in this case. So let's plug in those numbers. M is 0.6 kilograms. G is 10 meters per second squared. And D, so it's going a distance from 6.1 meters above the ground to 1.5 meters above the ground. So the direction is taken into account with the angle. So we just need the magnitude of the displacement. Let's make that a little better, which will be 4 27.6 meters. And if we multiply that together, we get 20, let's see, my cheat sheet here, 27.6 joules. 27.6 joules is done by gravity on the ball. What is the gravitational potential energy of the ball relative to the ground when it's released? So the gravitational potential energy is mgh. 0.6 kilograms times 10 meters per second squared times the height when it's released, which is 6.1 meters, gives us 36.6 joules. Same kind of thing. Find the potential energy when it's caught. Still 0.6 kilograms, still 10 meters per second squared. When it's caught, it's at 1.5 meters. So at that point, this gives us a 9 joule potential energy. The last one says, how is the change in the ball's gravitational potential energy related to the work done by its weight? So the change in the potential energy, the final potential energy minus the initial potential energy, will be 9 minus 36, or negative 27.6 joules. And notice the work is positive 27.6. This equals negative the work done by gravity. So the change in potential energy is equal to negative the work done by that force. One more potential energy problem. You're in a hot air balloon at 800 meters above sea level. The mass of the basket and its passengers is 700 kilograms. What is the gravitational potential energy of the basket and its passengers relative to sea level? So if sea level, this is not a perfect picture for this problem, but I'll say sea level is here, and the balloon, let's use red maybe, the balloon is up here at, and this is 800 meters, I believe, meters. So when we calculate the potential energy, it's going to be the mass, 700 kilograms, times g, 10 meters per second squared, times the height above sea level, which is 800 meters. And if we multiply all that together, we get 5,600,000 joules. It's a lot of potential energy. The next one says relative to the tops of the trees, which are 100 meters above sea level. So if the tree tops are here, tree tops, to go from the tree tops up to the balloon is 700 meters. So let's calculate the potential energy. So it's 700 kilograms times 10 times 700 meters, and that gives us a slightly smaller number, 4.9 million, or 4,900,000 joules. Both of those positive numbers. Now the last one says, find the potential energy relative to the record height for a balloon, which is 22,000 meters above sea level. I can't really do that to scale here, but I'll just say if this is 22,000 meters, h is going to be negative. It's going to be this distance. So we're going to use h equals, 800 minus 22,000, which is 21 21,800, no, 21,200 meters. And when we plug that in, we're going to get a, oh, I didn't put the negative. It'll be a negative potential energy of 148,400,000.